What? Okay. He's suggesting that I'm short. Okay. So, yeah, okay. So, uh, before I start talking about physics, and I see that I have a lot of students here, I want to tell you something. In in Brazil, is one of the places that I am. I am at the university, but I'm also at the ICTP, which is a chapter of the ICTP in Italy. But they have come with a new program, which is with funding agencies in Brazil and the Third World Academy of Sciences to us for to give fellowships to postdoctoral students, okay? Or I don't know how you call them here. Well, but those who have finished the doctorate. And it's not for every country, but Bangladesh is included, okay? So these fellowships are one of the programs, one of that is called, from a place called FAPESP to us, is for people working in the state of Sao Paulo. The other one is CMPQ to us, and that is for the whole country. Okay, so if you have any person in Brazil with whom you would like to do a postdoc, then you can write to them and check. Also, you have to check on the deadlines, because there was one a few months back, and it finished, and the only, I was looking for people, and the only person I got was someone from Menang in Africa. But I think I sent information here. I don't remember, but I may have forgot. But I thought I had sent the information here. And in those days, it was only FAPESP. But if you check that, and if any of you is interested to go and work in Brazil with some person, please, that's a possibility. I mean, they usually, this is, I don't know if I'm supposed to be telling people around this, but the fellowships from the state of Sao Paulo pay much better than the other ones. Okay? Okay, if you live in the city of Sao Paulo, it's also an expensive city, but you don't need to live in the city of Sao Paulo. You can be in other places. There are several universities in the States, so you can be in other places. Okay? So, well, I wanted you to know that, so you will see if someday you are interested to go to South America, we are welcome to receive you. So, then let's start about this talk. And I'm going to talk about phase transitions in sormalators, and which takes us into the XY model and a few other things. And so oh my Lord, it's not that clear because I wrote in white. Well, I have several collaborators. Here is a list of them. All of them except the last one, which is Fernando Ferreira, are from Cameroon. And the last one is from Brazil. And here you have a few pictures of swarmalators. Swarmalators represent essentially all kinds of animals that go together, in bunches, like it could be, as you can see, it could be insects, it could be fish, it could be other things. And so here you have something that maybe you have seen it. I don't know if here it can be seen, but in many places can. So these are these things called murmurations. And there are a lot of birds that fly together, and usually they do this before before they fly towards warmer places. So now, believe it or not, the one below, this one here, is not real. This one is the work of a Spanish photographer. Okay, so and what he has done, and he was able to get this kind of thing by looking at how they move, and then with some tricks of photography, he was able to do things. He's also uh, he's also very interested to interact with physicists to see if we can do something together. Okay, then what are swarmalators? I think this work was coined by Kevin O'Keefe, Hong, and Strogatz who were trying to represent this kind of systems, and they are systems of oscillators whose phase and spatial dynamics are coupled. So, and this is to describe the dynamics of a living system. So, what do I mean by the phase and the spatial dynamics? The spatial dynamics is the way they move in space. And the phase is something that we hope that we are describing, that these animals may have some sort of a brain, okay, small, big, I don't know how they are, with whom they interact, and the outer part interacts with the internal and vice versa, and how they move considering this type of systems. So, so we are going to study the effect that the internal dynamics has on the external dynamics, and we are going to find something that is being known, and it was already talked about today, called explosive synchronization. And what we are going to show is that this explosive synchronization, although it has, many people have talked a lot about it, is not necessarily a characteristic of the transition to synchronization. So therefore is not a necessary condition for the systems, because for a while this was considered the case. Okay, so then let's see when did we start? Okay, so then let's consider the kind of system that we have. The model is shown here. The model is shown up here. X sub I represent the spatial coordinates of the swarmalate of each individual of this set, and here we write only one coordinate, but you could have 2 or 3, depending on what the kind of system that you are trying to represent. Then it has an attractive interaction and a repulsive interaction, and then we assume that the interaction with the internal dynamics is given by this sort of Kuramoto-like of interaction, but it is let's say the coupling has a term associated to the spatial dynamics, which is given by this, and it does affect a lot what happens in the problem. So then the systems, usually one writes this type of equation with the first one has a velocity, depending on timing principle, which for the time being we are going to consider that is zero, and the natural frequency, which we are also going to consider to be zero. Okay, for the time being. So then this system has several, it has a rich structure. So what we represent here is in the upper part, it is the spatial representation of the particles. And in the lower part, we represent the internal variable. And in the upper one, the colors represent the internal dynamics. That is, I mean, here in the one below, I cannot. In the one below, we have put everything in blue, so you don't know which one is which. But in the upper one, for instance, here it tells you, that this bunch here, all of them have more or less, they are kind of together here in space, but they also have a similar type of, let's say, way of thinking. So if we can say that. So then the systems have, the first one is called async static, so or static async, depending on how you want to call it. So it means that that it is static that is static in space. Okay, this one is called active phase wave. It means that they have started moving. And as you can see, once you allow them to stop moving, they sort of tend to organize themselves. This one now, I made a mistake here how I put the figure, sorry. This is the third one. Here, as you can see, they organize themselves in the internal variable, because you can see that the colors get together, okay? Then the next one is called the splintered wave, because each part with the same internal variable, they get together in clusters and then they separate. And then finally they go to total synchronization in both space, and as you can see, all of them, they go static, and all of them have the same color, meaning that the phases are all equal, and you can see here that the phases are all equal. So let's see. Then how we analyze this system, as usually anyone in the area does, and we represent the essentially two variables, although I have three here, essentially two variables. A variable R, which is up here as Z equal R to the J phi, which is so-called the Kuramoto order parameter, and the Kuramoto order parameter represents the phases, the internal phases. The Kuramoto order parameter is something that is a variable that will be one when the whole system is synchronized. Like you can see here, the R is represented by the blue line, and is zero when they are completely desynchronized, that is, there is no cluster. These are the variables. S represents measures the correlation between the spatial variable, the spatial angle, let's say, and the and the one of the internal phase. So that is the phase, the spatial phase, and the internal phase. So, and as you can see, this variable S is the other way around. That is the Kuramoto or the parameter. It can be its maximum before when they are completely desynchronized, and its minimum when they are synchronized. Okay, so here we are representing for different values of the other parameters, but it's not what I want to talk about. So let's see. So let's see where I go. So the thing that happens is, if you remember here, if you remember this equation, the equation for the theta dot I, if I am near synchronization, the term xj minus xi in the second equation, the second term is xj minus xi is a constant, essentially, because they're being synchronized, they are quiet. It cannot be zero, okay, because they represent real objects, therefore they cannot be zero. So then there, when we are near that point, we can, I always, these things should be stronger. I cannot see it. Well, let's see. Let's pass to the other one. So here, look at the first equation. The first equation represents the energy of that system. Once you integrate that system, it has its tricks because you only got one equation, meaning you only got the spatial and the angle variables, but you don't have the momenta. So, but you can manage to integrate anyway. You can manage to integrate, and you can see that the energy of a particle is given by this equation, is the sum over all their neighbors of cosine theta and minus theta j. Okay, that equation, as you may recognize it, is the representation of the XY model in one dimension. Okay? And the representation of the XY model in one dimension, and we can really say, once we arrive to complete synchronization also in the phases, we get that AC is minus KC over 2, therefore the energy, the system loses energy by synchronizing. So, which maybe interesting in some cases. So then, what we saw when we were trying to see ¿qué pasó? When we were trying to analyze all these systems, we saw several things. First thing that we saw was that the order the system does is, as you can see, is complete disorder, then it starts in a splinter, start forming clusters, and until eventually form the synchronization. That is, the splinter state is one of the last one before synchronization. Okay, but then the point is, what about the synchronization? You see, the first figure that we got was this, and we were very happy. We say, explosive synchronization. Great. But then we started looking at the system with a little bit, with some more detail. And then we saw that really we were having, in some cases, a figure like the one you see, this figure like you see here, which doesn't look like explosive to me. It doesn't look like, I mean, you don't need to even do any math. I mean, it simply does not look like a first order transition. So then we started looking at the literature because being having a few years on me, I remember that one of the things that people like me remember from the time we were even students is that a first order phase transition, I mean, cannot, wait a minute, no, that there isn't a first order phase transition in the XY model. That's it. That was the theorem of Van Hove back in those days. So then we started looking at the problem. But then, is it the first order phase transition or is not? The first thing we started doing is looking at the literature. I mean, so we found many papers, but then I'm listing here some of the very important ones. One is by Cuesta and Sanchez, who lifted the ban imposed by the theory of Van Hove, meaning that we can have first or second order, it doesn't matter which. Then there was a paper of Pasot, saying that the Kuramoto model has the first order first transition from incoherence, complete incoherence, to synchronization in the thermodynamic limit, provided that the natural frequencies, those were the frequencies omegas that you write in the front, are evenly spaced or uniformly distributed in a finite range. Then there was another paper by Gomez Gardeñez and others who was quite famous at the time, and they have shown that a system like a Kuramoto model has an explosive phase transition whenever for a network that is scale-free and for a network that is scale-free, and when the distribution of natural frequencies is equal to the number of links. I mean, so if you increase the number of particles in the network, and the range where you have the frequencies is finite, one of the things that is going to happen, like it or not, is that the frequencies are going to be repeated, okay? So, and I'm saying this because there came a paper by Leiva and others who also was considered as having solved the problem completely, and in there they extended the results with when natural frequencies cannot be equal between themselves or to the mean. That means you could have explosive synchronization in that kind. But then doesn't apply to the case of Gomez Gardeñez, because the case of Gomez Gardeñez is if you go to infinity in the number of particles, and the frequency has to be equal to the number of links. Otherwise, you allow the number of links going to infinity, which usually is not done. So, or they are going to be equal, okay? And therefore, the Leiva case doesn't apply. Then there was a case in which Cardinal et al. Essentially repeated what Gomez Gardeñez did, except that they put some noise, and they said that the first order transition gets better if you put noise. There was another important paper here by Hong and Martens. They studied the phase transition in an XY model, which was a variant of the Kuramoto model for coupled oscillators. And they found that for the case without noise, the system seemed to have a first order phase transition, but if you have noise, this is not the case. This second case of noise, which it says is not the case, is the one that applied to our case. Because even if you, if the, we can consider, we can consider, let's go back to the main equation. We can consider this term 1 over xj minus xi, which I've been considering as a constant just to look at, to be able to integrate. Oh, no, I won't be able to finish. So, so the point is when we get here, this term before the transition to synchronization is essentially noise. Noise is where we are having the splinter case. And although I have considered it as a constant to be able to look at the energy, essentially it's noise, what we have in our system. So, since I've been told that I have to hurry, let's go. So, then what we did was we started looking at the problem for different cases of distribution of the energies. I mean, we have to look at the distribution of the energy. So we got out of our system, and what we considered was three cases. One when all the frequencies were random, another when half of the frequencies were random, and another with three different cases, one constant, another noisy, another noisy around the constant, and another completely random. And we found in all cases, in this case you can see, for instance, in this case you can see that the R is far from giving you synchronization, very near the transition, and the energy gives this distribution. The second case that I just told you we have here, and again, you don't find the first order transition here, and the energy also is shown here, and it shows that it's not a sharp transition. And the third case is what we have here, which is less than, it shows even less. So on our way to try to find the synchronization and other things, we found some interesting things that had not been seen before. And one of them is that you see we represent in the upper part the angle theta as a function of time, and in the lower part the distribution in space. And as you can see in the upper part, this is in theta, this is a rotational case. So you can see it here better in these drawings, and this is the angle theta, and you can see that this is moving around, and these other are also moving around in a different way. Since I want to show you something else, I'm going to stop with this one here. And what I wanted to show you is this. Remember that I said from the beginning that I was not going to consider. I said from the beginning that I was not going to consider the speed or the frequencies different from zero, although then I moved to from frequencies different from zero. But now what I'm going to consider is that the elements consider the previous velocity. That is, in two cases. One is they consider their individual previous velocity, and the other is they consider the average of the group velocity of the average of the velocity of everybody, and see what that could do. And what we saw was that if you look here, here, this is we start from this state, which we call it wing phase, although I haven't had time for that. And then what we are looking here essentially, when you put the velocities, is about is the repulsion of that or the attraction having any effect in the problem? And then what we have seen that although these effects are very slow, because we have done the videos of all this and they are extremely slow, you need a lot of patience to see it. And then here you see that there is one element that moves away. Eventually it moves back. But if you look at the differences in time, it's huge. Okay, so it's very slow, as I say, but eventually also they are attracted by the whole bunch of swarmalators until they are all synchronized. And this is for the case of the individual, considering that they are affected by the individual velocities, and in the case they are affected by the average velocity, you can see that we have different, although we are starting from different states, eventually part of it moves away, part of it goes back. And then in this case, you can see it's more complicated because the one that has in a way is dancing around this other one, but eventually it comes back. Although you may think we are crazy, we have called this the mother duck effect, because because you can find videos in the internet of little ducklings with a mother duck, and when one of them separates, you see something exactly like this. So this is what we call the mother duck effect, and I'm not going to spend time in the conclusions. I'm just going to thank you for your patience, and well, hope you enjoy.
Hello, thank you, Hilda. So this is now open for questions. I have a few questions. First of all, whether your results are size dependent.
Sorry, since you're behind me, I don't hear so well, so I'm coming near.
Oh, so is the results are size dependent?
Independent.
Size dependent.
Size dependent. Okay. The results, can you hear? No, the results, no, as soon as you pass big numbers, like 50 or so, they are not size. They don't depend on the size.
They are robust to that smaller size.
Yeah, I mean, we've been working with 50 most of the time,
Okay.
but the results don't make any difference.
But okay, so then you assume that the velocity is updated.
Sorry?
Velocity is updated.
Yeah.
The previous one
Yeah,
you were
in the
taking.
last cases was
In last
updated.
cases, but the frequency remains zero, right? So what could be if you have a heterogeneous system?
We have left the frequency fix. We have left the frequency fix.
So
yes.
we have not studied the.
The point is that the amount of details, they are too many. You see, and it went again. The amount of details are too many, and essentially let's say the frequency affects the Kuramoto model. Mm-hmm. Okay, so and the Kuramoto model and it's how you change the frequencies in the Kuramoto model. It has been studied by many people.
Yeah.
So I mean. We didn't think it was, although you see, Although we did change the frequencies when we checked the second order phase transition. In that case, we did. Yes.
Any other questions? If there is no other question, let us thank the speaker once again and we move to the next speaker. So our next speaker, Kamrul, the next speaker is S.H. Nakib. Oh, so we can invite, okay, Professor Nakib. Saleh Nakib, okay, okay, okay. So, high temperature cuprates, where is the glue? His title. Now the on.
Right on. Assalamu alaikum and a very good afternoon to you all. I would like to start by thanking the organizers for giving me this opportunity to be present in this grand event and also giving me the opportunity to talk about high tissue cuprates. Today I'm going to talk about superconducting copper oxides. And the question I am going to ask is, what is the glue? So before starting, I would like to say a few things about high tissue cuprates. These are the systems that was discovered in 1986, so it has been almost 40 years. Still, there are many unresolved issues regarding the physics of high tissue cuprates. And one of the prime question is, as you know, to get superconductivity, you need Cooper pairing. And that happens when there is an electron boson coupling. Ordinarily, this boson is phonons, but theoretically you can build formalisms where phonons are replaced by other type of bosons. In case of high tissue cuprates, this is still an open question. What is the glue that is leading to electron pairing in these strongly correlated systems? And today I will focus on that. I must acknowledge my co-workers, Dr. John Loram of University of Cambridge, Professor Jeffrey Lewis Talon, he's from New Zealand. He was with McDiarmid Institute and Victoria University, Professor John Robert Cooper, my PhD supervisor, and Professor Raihan Islam sitting there, my colleague, and both of us, we worked under the supervision of Professor John Robert Cooper, who is now an emeritus professor at Cavendish Laboratory. So they all have contributed significantly to the results I will be showing today. So I acknowledge their contributions. Okay, so why bosons? As I said, to get superconductivity where you have electron pairs, and this happens when the Coulomb repulsion, as you know, two electrons, they feel Coulomb repulsion. This repulsion is overcome by some effective attractive interaction, and that attractive interaction comes from lattice polarization, and that is phonons. And you can also, as I said, you can also imagine other bosons like the magnons. They are contributing to the formation of Cooper pairs. So the bosons are the carriers that lead to superconductivity. And why high tissue cuprates? Because this is one of the most interesting systems in the field of strongly correlated electronic system. And there is definitely other reason, and which is very obvious. It has to be bosons I'm talking about here, because this is about Bose-Einstein statistics, and we are remembering the legendary Satyam Bose. So I have to pick a subject where bosons play a very important role. And you can see the paper, the groundbreaking paper here. The German version is placed beside the English version. And I would request all the students to go through this paper at least once in their lifetime. This is really worth doing. And why high-tensor cuprates? As I said, they are the most famous among the strongly correlated electronic systems. And they're definitely the most widely studied condensed phases which belong to strongly correlated systems. And discovered in 1986, the basic physics remains unknown till date. And this is one of the grand challenge in condensed matter physics. So if you select 5 or 10 outstanding problem in physics, you will see that invariably the physics of cuprates is listed there. I'm not going through this. This actually tells you why the problem is so profound, because in copper oxide superconductors, there are many different energy scales are at play, and the ground state of this particular electronic system is hard to define because of so many competing and sometimes cooperative electronic correlations. Okay, so this is the electronic phase diagram of copper oxide superconductors, and I would just spend a minute on this. This is hole doping. This is where you dope the system. When you don't dope it, that is the undoped parent system, that is antiferromagnetic insulator. And as you dope, you can dope it via different techniques. As you dope, the antiferromagnetic order goes away at a certain doping, and you come to this point where superconductivity emerges, and it varies like this with hole doping. In addition to superconductivity, you have incommensurate charge density wave. There is anomalous normal state, which does not conform with Fermi liquid, where you have the resistivity going linearly with temperature. And you also have spin density wave in this region. And when you go in the overdoped side, by overdoped I mean you get to the hole doping where the maximum of superconductivity has been exceeded in this side. It becomes kind of Fermi liquid-like, but it has some properties which are not exactly like Fermi liquids. So this is a very serious challenge, because I think you know that the standard model for condensed matter physics is the Fermi liquid theorem. In addition to many exotic properties in the normal state and in the superconducting state, you also have a D-wave order parameter. The order parameter changes sign within the Brillouin zone, and there are places where the superconducting gap vanishes. These are called the nodal points. At the antinodal points, these points, you have the maximum of superconducting gap. In ordinary superconductors, which we call the BCS superconductor, the order parameter is S-wave-like, that is spherically symmetric. But for copper oxides, the order parameter has different symmetry. Okay, but still they are superconductors, so there must be common features, and the common features are these. You need phase-coherent Cooper pairs for superconductivity, and that will lead to a Fermi surface instability. And this instability will open a gap centered around the Fermi level in the quasi-particle excitation energy. And all these three factors are seen in copper oxide superconductors, like the ordinary BCS, Barden-Cooper-Schiffer superconductors. Okay, so microscopic theory of superconductivity. This is, to me, one of the most influential papers in the history of condensed matter physics. And this appeared in 1957. This thing should be noted that superconductivity was discovered in 1911. So it took 46 years to get a microscopic theory of superconductivity. And you will be surprised to know all the very big names in physics including Einstein, Bohr, Landau, Heisenberg, Pauli. They all tried to figure out the theory of superconductivity at some stage of their life or other. They all tried. So I think you can imagine the magnitude of the challenge that after discovering the phenomena in 1911, it took 46 years to get to a microscopic theory. So we are also counting days because copper oxide superconductors were discovered in 1986. It is almost 40 years. And with all our modern formalisms and all the tricks in the trades in condensed matter physics, we are still to figure out what's actually going on there. Okay, so there are two very basic equations. These equations are also kind of fundamental, except for minor modifications. All superconductors show a gap structure, and in BCS superconductors, the superconducting transition temperature actually depends only on two special parameters. One is the characteristic energy of the phonons. We call it Debye temperature. And the term you see in the exponent altogether, this gives you the electron phonon coupling constant. If you think about bosons of other type, there will be modifications, but the form will remain, we expect, pretty much like this if it is weakly coupled. And this would be, instead of electron phonon coupling constant, we'll call this electron boson coupling constant. And that boson is the focus of today's talk. We need to know what are the bosons, or what is the boson that lead to Cooper pairing in copper oxide superconductors. Okay, so we need to look at bosonic fingerprints. And in the earliest day, the most clearest indication of phonons as the bosons leading to Cooper pairing came from isotope effect. What people observed that if you take an elemental superconductor and if you replace the element by one of its isotope, the superconducting transition temperature becomes different. So that was the first and very strong signature that phonons are involved. As you know, the frequency of the phonons, they are dependent on atomic masses. When you substitute one isotope with another, the major change that comes about is not in the electronic band structure. The major change is in the phonon spectrum because of the mass difference. And as this mass difference leads to a change in the superconducting transition temperature, that gave you the first indication that phonons are involved in Cooper pairing and eventual appearance of superconductivity. In copper oxide superconductors, people did these phonon experiments, and we have done it extensively. And for isotopic substitution, we have used O16 and O18. So basically, when we make copper oxide superconductors, it's mainly oxygen 16. In carefully conducted experiment, we can exchange almost 95% or 98% of this O16 with O18. And we track the superconductivity, what happens to the superconductivity as we substitute the oxygen with heavier isotope. And this, the result we receive is very strange. I'll get to that. There is another indication of coupling of electrons with some bosonic degrees of freedom. And it comes from the electronic dispersion relation. There is a kink, and this is clearly shown in that very good textbook, Solid-State Physics by Ashcroft and Mermin. You can see it here. This is the electronic dispersion line, this one in the middle. But once it becomes distorted like this is a clear indication that the velocity of the quasi-particles, say the electrons, which we have in the periodic lattice, they are changing. And what is bringing out this change? This is the coupling between electrons and some bosonic degrees of freedom. The energetics and the energy dispersion becomes distorted when it couples to a bosonic degrees of freedom. And for electron phonon system, this region over which you can see the distortion, that gives a measure of the energy of the bosons that is affecting this dispersion. So in morning session, Professor Jahid Hassan talked about RPS. When you use RPS, you can actually, the technique has advanced so much. If you look at the electrons which are photo-ejected, you can actually find out from which orbital, with which K value, and from which part of the billion zone it is coming out. And if you map that result, you can see in copper oxide superconductors, there is actually kink there. So something is coupling with a bosonic mode, and that is quite conventional. But identifying this particular bosonic mode is a challenge. These are all those RPS results, and in all those figures, you can see the kink in the electronic dispersion. And from this dispersion, it is also possible to calculate the electron boson coupling constant. So very roughly, if the kink is very strong, the coupling is also very strong. So that happens in copper oxide superconductors. And here, from the RPS, if you do a very careful analysis, you can find out the electron boson coupling constant, and it has a doping dependence. You should remember the electronic phase diagram. It starts like this, then it rises to top, and then in the overdoped side, it goes down. So, in the underdoped side, this is less doping. The electron phonon coupling constant is, electron phonon, I shouldn't say, the electron boson coupling constant is quite strong. And with increasing doping, the electron boson coupling constant is going down. And this is, it has many factors which need to be explained, and I will try to touch it. Okay. So there are many papers. This is one review type. So this is actually the paper is also related to the bosons responsible for Cooper pairing in copper oxide superconductors. The possible candidates are many: magnons, phonons, bipolarons, plasmons, and there are, you can think of much exotic excitations come from quantum critical point where there is entanglement and the ground state is non-trivial. There are other orders like the charge density wave, spin density wave. Dynamic strife phase is a very prominent candidate. There is d-density wave, paired density wave, etc. So there are dozens and dozens of theoretical formalism, but non-conclusive, which can really tell you exactly about the bosons that are at play. What we have done, we have measured the oxygen isotope effect, and you can see it here. This is the oxygen isotope effect. In the underdoped region where the superconducting TC is low, you have a very high isotope effect. But very strangely, where the superconducting transition temperature is maximum, the isotope effect is very low. And this low value of the isotope exponent persists in the overdoped region. So what actually we are looking at? When the electron boson coupling constant is strong, the isotope effect is strong, the superconducting TC is low. You don't expect it because, in the exponential factor, when the electron boson coupling constant is high, you automatically expect the superconducting transition temperature will be high. But you see nothing like this, especially when the TC is maximum, the isotope effect is very, very low. So what actually is happening, and that is the question I'll try to address. So since we see an isotope effect, we have to admit that phonons are involved. But to what extent, that is the question. Because you have a huge isotope effect, very large electron phonon coupling constant in the underdoped side, but the superconductivity is very weak. Now, this is not the ordinary BCS picture. There is something serious going on there, and which is not conventional. So again, I'm summarizing. You can see here the electron phonon coupling constant is high. You are staying in this region, but this is superconducting transition temperature. This is low. The oxygen vibration has a large effect on superconductivity. So naturally, you would expect the phonon is present, but superconducting is in fact a bit suppressed where where phonon is giving a large isotope shift. So what is the solution? And as I said, the strong electron phonon coupling seems to inhibit superconductivity. Our understanding is the coupling we are seeing via the isotope exponent experiment is actually related to this charge and spin density wave. If it is not commensurate with the lattice, then what will happen when you have a charge order or spin order inside your system? There will be a very strong electronic and lattice degrees of freedom. They will affect each other very strongly. And this is kind of electron phonon coupling constant, but the context is completely different because now we are talking about spin density wave and charge density wave. And this kind of order actually never helps superconductivity. And almost always when you have strong charge density wave in a system, you will see superconductivity is getting suppressed. But if you have charge density wave, you must have, well, must is a strong word, but you expect there is a very large coupling between the lattice degrees of freedom and electronic degrees of freedom. And that would lead to a very high isotope effect. So the large isotope effect we see in the underdoped region and large electron phonon coupling constant we see in the underdoped region where the superconducting TC is low, it is actually not directly related with superconductivity, but this is related with charge density order or spin density order. So that was our understanding. And what we do, we make a prediction. We thought if that is the case, there must be a correspondence between spin charge ordering temperature and isotope exponent. Because if the isotope exponent I get is mainly connected with charge and spin density wave, then anything that enhances or destroys the charge density wave or spin density wave order, that effect will be reflected in oxygen isotope effect. And we have checked the literature, and this is what we get, and this is, to me, this is very exciting because this is what we have found. In this one, this is the isotope effect, the red symbols. And these are the melting temperature for the spin order and charge order. Above this temperature, you really don't see the strong signatures of charge order or spin order. So what we see, the isotope exponent that we have measured for copper oxide superconductors, they are completely related with charge ordering energy and spin ordering energy. So the effect is there, but the isotope effect we get, it is not describing the electron phonon coupling that is leading to Cooper pairing. This is something else. Okay, so if we summarize the results that I have shown till now, since there is an isotope effect in the overdoped region, though the isotope exponent is very small, it is still there. I must say that in the overdub region of the electronic phase diagram, there is no sign of spin or charge density order. The spin and charge density order they only exist in the underdub region. So in the overdub region, we get a very small isotope effect. So what will be the implication? The implication is this, that phonons actually contribute to superconductivity. But that contribution is very much low from what you expect from ordinary BCS-like superconductors. The isotope effect we get in the overdub region, which I would say the intrinsic isotope effect, which is not related with spin and charge density wave order, it is something like 0.1 or even 0.05. In canonical system, the isotope exponent is 0.5, so 5 times to 10 times lower. So this is partly responsible for Cooper pairing, but the contribution is small. So we have high temperature superconductor, electron pairing must be there. Phonon is playing a minor role. There must be other bosons which is contributing to the superconducting transition temperature. So we call it multiple pairing channel. And there are some indications that spin degrees of freedom, in addition to the lattice degrees of freedom, both contributes to pairing in ITC copper oxides. So the conclusion we can draw that in copper oxide superconductors, it will not be very productive to expect that a single type of boson is playing the role to bring about the Cooper pairing. We think the situation is mixed. Multiple degrees of freedom are coupled with electronic degrees of freedom. For example, the spin waves, it's there. Short-range antiferromagnetic order persists over quite a significant region of the electronic phase diagram. These fluctuations, together with phonons, they lead to the superconducting pairing in high TC cuprates. So that has been our point, and we have looked at different scenarios, and our feeling is there is DOA pairing, and the pairing has both magnetic and non-magnetic contribution. From phonon, the non-magnetic contribution is coming. The ground state, as I said, is antiferromagnetic insulator, and as we dope, the long-range antiferromagnetic order vanishes very quickly, but there are remnants of short-range antiferromagnetic order. And that order can play a significant role to bring about pairing between the electrons. So that's all I wanted to talk. Thank you very much.
Open for questions. Yes, please. Micro it's not switched on.
Thank you very much for insightful talk. Actually, you might have looked this optical as well as acoustic both phonons, because in conventional BCS theory, they did not take into account of optical one.
Yeah, actually, we did what we did. This was an experimentalist job. When we substitute O16 with O18, actually the whole of the phonon spectrum of oxygen atoms, they change. And if you look at the structure, you have a copper oxide plane,
yes,
and there is one apical oxygen, as we call it. It is on top of a pyramid. You have 4 coppers here,
yes,
and 1 copper sitting on top. And it is constructing something like a pyramid. And all the charge transfer and coupling to the vibration of the electrons within the copper oxide plane, that happens through the apical oxygen.
yeah.
And from Raman and other spectroscopic techniques, we know the kind of modes they generate. And the common understanding is if phonons are involved, the most important part is played by the apical oxygen.
Yeah.
So information about their vibrational spectrum is completely known. And we use that and we translate what happens with isotopic substitution. So actually, we are not looking any particular phonon mode. We are looking at the overall effect
Yes.
of isotopic substitution.
Okay.
Any other question?
Yeah, sure.
Yes.
Okay, further, my further very small query is, yeah. You were talking about Magnon's role also. You were talking about role of Magnon.
Yeah.
But previously, okay, before 2008, we were thinking that, okay, Magnons destroy, iron destroys this superconductivity like this. So in YBCO also, you are seeing this Magnons and then...
The thing is, you see, if you look at cuprates,
yeah.
you can have a maximum TC of 38 degree,
Yeah.
and you can also have say for LESCO, you have a maximum TC around 38 degree. But if you look at the mercury-based system with 3 copper oxide layers, that superconducting transition temperature goes to 164 degree Kelvin under pressure. But the generic thing is, if you look at the electronic phase diagram, all those families show almost the same electronic phase diagram. So what we believe, since the electronic phase diagram is very similar, irrespective of the maximum superconducting temperature, it starts when the antiferromagnetic order goes, it rises to a maximum value, and with overdoping, it goes down. It happens to all the superconducting systems. So, it will be natural to assume the superconducting mechanism in all the cuprates have some common roots. That's because irrespective of the superconducting transition temperature, the phase diagram looks the same.
Same, yeah. Thank you.
Hilda?
Thank you. Can you hear me now?
Yeah, I can.
Yeah.
Yeah, okay.
Sure.
Okay. I mean, sorry, I'm not in the field. I just want to talk a little bit about history. The part of Cooper in the BCS theory had been downplayed constantly throughout history. Okay? So, I don't know why. Well, by the way, I don't know if you know, he passed away last week, Cooper. It was the only one who was alive from the 3 of them. The thing that I want to say is, I don't know if you have gone to the original, but it was his work, the one
true.
that made the whole work possible. So, and he was not a solid-state physicist. He was a high-energy physicist. Okay? So he had, obviously he had this idea that if he would have discussed the idea with solid-state physicists, he may have forgotten, because people would have said immediately, "Oh, you're crazy. I mean, what kind of idea are you coming from with?" So maybe it's something more or less like that, a little bit wild, is needed again. You see? Because, as you say, almost 4 years ago was his conference. So, thank you very much. Very nice talk.
Yeah,
brother.
thank you so much. But you see, we call superconductivity is coming from Cooper instability. So we remember him, but not probably as much as we should. And there's another thing. If you look at the stripe phase, where charge-rich region and spin-rich region are separated, it is very much, it looks like the patterns you have shown. This is actually self-organization, and there is this critical exponent there. So you are actually quite close to some part of the phase diagram of copper oxide superconductors, because it happens spontaneously, the regions separate, and it happens like this, as you showed when the swarms move and kind of phase transition takes place. So we are all connected actually.
Assalamu alaikum, sir. My question was, the theory of Cooper pairs were formulated for very low temperatures, right?
Sure.
So for high temperatures, are we still assuming Cooper pairs to be the only factor, or are we looking into a different explanation or an extension of the theory?
Yeah, it's a very good question. You see, we do certain tests. One is Meissner effect, okay? And we set a persistent current. And we measure flux quantum. These are very basic experiments. And if you do those experiments carefully, you can see directly whether the charge carriers are pairing. So there is absolutely no doubt the charge carriers electrons are getting paired. So the natural thing is what should we call that pair? And there is no reason not to call them Cooper pairs, because in terms of those experiments, there is absolutely no difference between BCS superconductors or even hydrides, under high pressure. Now we have superconductivity above 200 degree Kelvin. And there are Cooper pairs. So it is actually about energy scale. If you have very high energy bosons, I show you the TC equation, you already have an enhancement in the TC. At the same time, if you have very strong electron boson coupling constant, not related to spin density wave or charge density wave, you expect superconductivity at very high temperature. The problem is when you have very high electron phonon or electron boson coupling constant, it puts enormous strain to the lattice, at least in form of electron phonon coupling constant. If it is very strong, the structure changes. And if the structure changes, all your calculation is gone. So that is one big problem. You cannot increase the electron phonon coupling constant or electron boson coupling constant indefinitely, keeping the structure intact. So that is a big problem.
Professor Nakib, I must thank you for one reason. So you finished your talk within 25 minutes, allowing the other people to question. So this is the standard. If you given a 30 minutes, 25 minutes a talk, 5 minutes for the remainder. Thank you for that point. Okay, I share my personal experience. I was writing a review on dynamics in Josephson junctions very recently last year. Yeah. Since my master's, I know that the BCS theory. I didn't ever gone through the details of it, but I know that the BCS theory is the basic theory of the superconductivity. But when I writing the review on the dynamics of Josephson junctions, then I find the onus is they actually experimented on the first 1911. He did the first experiment on zero resistance. With this personal note, I thank you, and thank you all who are present here and all the other speakers here in this session.
Thank you very much.
Thank you.